Hello everyone, and thank you for joining us today. Micromeritics is excited to introduce a new feature on our TriStar and 3-flex gas adsorption instruments that will allow users to obtain free space measurements with alternative gases to helium. In this presentation, we will briefly go over the basics of free space, the advantages of this new option, and how to use it. Lastly, we will also review data collected using the new feature. Free space, also called void volume, is the volume in the sample tube that is not occupied by the sample. It is a parameter for calculating adsorption quantities, which is needed to calculate specific surface area and pore volume. The amount of gas adsorbed is calculated by subtracting the remaining quantity in the gas phase, which did not adsorb on the sample, from the total dosed quantity. To accurately determine the residual gas, free space must be obtained. Helium is traditionally used since it does not interact with most materials and does not condense at the analysis temperature. Micromeritics gas adsorption instruments offer 3 different ways of determining free space. Direct measurement of free space is most accurate and reliable. The method, however, does extend analysis time and consumes helium for each sample analysis. Free space can also be entered if the values are known, for instance, from a previous analysis using the same sample tube with the same sample. Lastly, free space can be calculated from knowing the volume of the empty sample tube and the volume of the sample, calculated from its mass and density. The new sample tube free space feature uses this method, which we will go into more details later. Let's take a look at how free space is obtained on the Micromeritics, TriStar, and 3-flex instruments. This process involves 2 distinct measurements: ambient or warm free space, and analysis or cold free space. Ambient free space is determined at room temperature with the dewar down. The calibrated manifold and sample tube are first evacuated to remove all gas. The manifold is then pressurized with helium to slightly above atmospheric pressure. Pressure is measured using a pressure transducer, and temperature is monitored. Gas is allowed to expand into the sample tube, and pressure and temperature are again monitored. The pressures in the manifold before and after dosing are used to calculate ambient free space, which is corrected to standard temperature to determine the effective sample tube volume, excluding the volume displayed by the sample, which is the capacity of the sample tube to store gas at standard temperature and pressure. In this simplified equation, F sub W is ambient free space at standard temperature and pressure. V sub m is the manifold volume, T sub m is the manifold temperature, P sub 1 and P sub 2 are the manifold pressure before and after dosing, respectively, and T naught is standard temperature. Subsequently, analysis free space F sub C is measured with the dewar typically containing a cryogenic liquid, such as liquid nitrogen, raised with the sample tube partially submerged. Pressure in the sample tube is measured again, P sub 3, and analysis free space is determined. Analysis free space will be greater than ambient free space because as temperature decreases, particles slow down and lose kinetic energy. As a result, the gas molecules have less energy to move around and collide with each other or the sample tube walls. This decrease in kinetic energy leads to a drop in pressure, allowing more gas to occupy in the same physical space at standard pressure. Using the ideal gas law, the instrument calculates how much gas can fit into the sample tube at the same pressure when the temperature was at ambient. Therefore, when the sample tube is colder, more gas can fit into the same given volume at the same pressure. There are 2 zones in the submerged sample tube, a warm zone and a cold zone. The warm zone is the head space of the sample tube not immersed in liquid nitrogen nor covered by the isothermal jacket. This portion is exposed to the warmer ambient temperature. In contrast, the cold zone is the portion of the sample tube and sample that are at analysis bath temperature. The ambient and analysis free space values are used to calculate the cold portion of the sample tube, and compressibility factors used to correct for non-ideal gas behavior at low temperature. Sample tube free space is a new addition on the Micromeritics, TriStar, and 3-flex instruments that uses the calculated free space method. Free space is obtained by subtracting the quantity of gas displayed by the sample from the empty sample tube free space. The volume that a sample occupies, and thus the volume of gas it displaces, can be calculated by dividing the sample's mass by its density. With the new feature, the volume of an empty sample tube can be determined using gases other than helium. The default gases offered in the new feature include, but are not limited to, nitrogen and argon. Any gas can be used if its adsorptive properties are known and it does not interact with the sample tube or instrument components. Depending on the specific gas, the TriStar uses non-ideality factor or compressibility factor to correct for non-ideal gas behavior, while the 3-flex uses compressibility factor for all gases. In the equations seen, N is the quantity of gas, P is the gas pressure, V is for gas volume, R is the gas constant, T is temperature, alpha is the non-ideality factor, and Z is the compressibility factor for the gas at a specific pressure and temperature. This new feature allows the operator to use alternative gases to helium to determine free space. Why is this advantageous? Helium is considered scarce due to its limited natural reserves and widespread demand across various applications. Its high cost stems from the challenges associated with mining it and its status as a non-renewable resource. Once helium escapes into the atmosphere, it cannot be recovered. Additionally, any disruptions in the handful of countries producing helium can greatly affect global supply, similar to what we recently experienced. Price fluctuations are common due to its availability, and the overall expense continues to rise with decreasing supply. Gases such as nitrogen and argon are abundant in the atmosphere and can be separated relatively easily. Therefore, they are more readily available. Nitrogen and argon also are cheaper than helium and can offer substantial cost savings. Utilizing gases other than helium also provides operators with the flexibility to employ gases that are easily accessible within their laboratory environment. To use the sample tube free space feature, we would need an empty sample tube fitted with the same accessories used for sample analysis. There might be slight differences in filler rods and check seals, causing their volume to be different from one another. Isothermal jackets help keep temperature constant in the sample tube during free space measurement and subsequent analysis. Keeping the accessories identical will ensure consistency in free space determination, mitigating any potential differences resulting from using different configurations, as slight variations in volume could impact the precision of calculated free space values. The steps to use the sample tube free space option is the same for both the TriStar and 3-flex instruments. We will navigate to the unit menu, then select sample tube free space. At the next window, select Default in the Method drop-down menu and choose your gas. Next, click New to create a new sample tube file. Give the sample tube a name and select any accessories used. These do not affect the free space values and are for reference only. Click Save As to save the sample tube file. It's important to note that the bath temperature should be recorded correctly, as this will affect the free space values determined. Click Start to begin sample tube free space measurement. During analysis, the valve to the chosen gas will open instead of the traditional helium. In this TriStar example, The manifold is being pressurized with argon as the selected gas. To apply the sample tube free space for analysis, in the SMP file under the Sample Description tab, select the Calibrated Sample Tube from the Sample Tube drop-down menu. It's important to enter an accurate sample mass and the material's skeletal density, which can be found in literature or measured by gas picnometry to determine the sample's volume. Under the Analysis Conditions tab, click on Free Space, then select the Calculate option. Save the SMP file and begin analysis as normal. During testing, direct free space measurement will be skipped. To test the new software feature, empty 1/2" and 3/8" TriStar sample tubes along with 9mm and 12mm 3-flex sample tubes were calibrated with and without filler rods using helium, nitrogen, and argon gases at liquid nitrogen and liquid argon temperatures, with each condition analyzed in triplicate. The free space values obtained from calibrated empty sample tubes were applied to reference material analysis to evaluate if results obtained meet predetermined specifications. 2 Micromeritics alumina reference materials were selected for testing. Both have low specific surface area, with one measuring 0.2 square meters per gram and the other 5 square meters per gram. Low surface area materials were chosen because free space has a greater impact on results, since displacement of the adsorptive gas can be greater than uptake, thereby magnifying the influence of free space. Additionally, there are specifications for the reference materials, making it easier to assess if analyses using calculated free space would yield results as expected. The 0.2 square meters per gram alumina reference material was degassed at 400 degrees Celsius for 1 hour, and the 5 square meters per gram was degassed at 350 degrees Celsius for 1 hour. Skeletal density values for each was obtained by helium picnometry on the Micromeritics AccuPic. The alumina reference materials were analyzed with free space measured as well as free space calculated with helium, nitrogen, and argon. We are now going to look at some of the test results obtained for a commonly used combination of sample tube, analysis gas, and bath for each the TriStar and 3-flex. The top plots show the results obtained for ambient and analysis free space values in empty 3/8" TriStar sample tubes with no filler rod analyzed at liquid nitrogen temperature. Using helium as the benchmark, the table below shows that the relative percent difference for each is less than 1%. The same empty 3/8" TriStar sample tubes were remeasured at liquid argon temperature. Using helium for comparison once more, the table below shows that the relative percent difference for each is also less than 1%. We have here an isotherm overlay of the 0.2 square meters per gram alumina reference material analyzed with free space measured as well as calculated on the TriStar. The difference may look great, but that is because the scale is very small and magnified. This plot illustrates BET surface area results for the 0.2 square meters per gram alumina reference material against how free space was determined. The data points indicate a very close alignment, with all falling within the specified range. Calculated free space values for the reference material analyses were compared with the free space measurement using helium. The relative percent difference for all values is less than 1%. Next, we have the results obtained for ambient and analysis free space values in empty 12 mm 3-flex sample tubes with check seals and filler rods analyzed at liquid nitrogen temperature. Again, using helium to compare, the relative percent difference for each is less than 1%. The same empty 12 mm 3-flex sample tubes and setup were remeasured at liquid argon temperature. Once more, utilizing helium as a point of comparison, the relative percent difference for the measurements is around 1%. This is an isotherm overlay of the 5 square meters per gram alumina reference material analyzed with free space measured as well as calculated on the 3-flex. This plot displays the BET surface area results for the 5 square meters per gram alumina reference material against methods used to determine free space. All data points fall within range. The measured free space values obtained during the reference material analyses using helium were compared against the calculated free space measurements, and we see once more the relative percentage difference for all values is around 1% or less. Another advantage of using calculated free space is the reduced overall analysis time compared to if free space is measured. The empty sample tube only needs to be calibrated once and can be used for all future analyses with the same sample tube. In this example, on the 3-flex, using 12 mm sample tubes, we see here that using calculated free space shortens the total testing time by about 25 minutes. In another example, this one on the TriStar with 3/8-inch sample tubes using calculated free space results in a reduction of approximately 30 minutes in total analysis time. In summary, the new sample tube free space feature offers a quick method to calculate free space values on the Micromeritics surface area analyzer system, eliminating the need for helium. Calculated free space generates consistent results comparable to direct free space measurement with negligible difference and faster analysis. This alternative approach not only saves time but also reduces costs. Thank you for attending our webinar today.